Hey everybody, welcome to more conversation about home performance. In this session, I'm going to be teaching you why load calculations are important and how they work, basically how to look at them. When we talk about home performance, I always like to couch things in terms of the enclosure, which is the skin of a home, and the engines, which is the circulatory system of the home, anything that moves heat or air. The big part of that we're going to be talking about today is heating and cooling, and also dehumidifying, and also ventilation, and also air leakage. All this kind of wraps into the conversation about load calculations, or what the pros in the biz call load calcs. So today, whether you're a homeowner or a professional of some kind in the building industry, this should be helpful. I'm going to break down for you what a load calc is, what it looks like, the actual report, why it's important, it's incredibly important, and also how to look at them. I'm going to take you on a tour of a few different load calculations that I've done on some really interesting projects, and you'll kind of see how they work and why these variables become very important. So the first thing to understand is that I am talking to you right now from the world's highest performance tiny house on wheels. Tiny houses, not generally a very good idea. Tiny houses also really interesting when you want to talk about load calculations. Most people have no clue about how this works. I will show you in a few minutes. So this house toured 13,000 miles. We still sleep here while we're building a big house. You can tune in about all that stuff at our YouTube channel, which is Home Performance, if you're not already a subscriber there. But this place is kind of special in a couple ways, and we built it to show people this exact thing that we're going to be talking about today. So this is what it actually looks like in real life from the model, and the model was important. We always model, and modeling is what we are talking about ultimately today. But of course, the real life thing, you want to prove that it actually works the way that the model says that it's going to, and that also is what we're talking about today. So right now, I'm in the process of building a house that I modeled in 3D that is a 3,000 square foot house for my family. We're not going to always live in 200 square feet. That's just not very sustainable. And so we're in Atlanta. This house has 2 levels in some places. It's got high ceilings in other places. It's got windows in some places, no windows in other places. So we're going to get into all that. It's also a pretty interesting project when we're looking at it. And here's what it looks like in real life as we stand right now. Next thing that we're doing is finishing out this roof. But the load calculation was very important for getting us to the conversation of duct design, which we just completed, and I will be doing a separate video about that. That's a totally different topic. Now, if you like what you learn here, there is a lot more for you. Obviously, this video is part of our over 500 videos on the Home Performance YouTube channel. We have a downloadable Proof is Possible booklet, which is a 24-page, basically full-color photo magazine that we put together just to teach people how all of the home as a system thinking works. That, obviously, you can find at buildingperformanceworkshop.com, along with all the rest of these things. We have a course, it's called a crash course. That's kind of for people who are new to home performance. That's pretty inexpensive. We have a book on how to do every test that you would essentially want to do in any home to verify all of the things that we're about to discuss. I have a reporting software that I built called Apt Reports, which stands for Automated Performance Testing. That's kind of cool. You can find that out at the website as well. And then the kind of crown training that I have is my 6-week mastermind course, which is self-paced. It's all online. It involves monthly coaching calls with me, and we get all the masterminds together. These are people who are around the world who are becoming the cream of the crop of the entire construction industry. So, first piece of this puzzle is, what is it? What are we talking about? When somebody says a manual J or a load calc, what exactly do they mean? So essentially all it is you've got this skin, this enclosure that you have planned in the case of when most people want to be doing a manual J. In this case, we're looking at, the truck. Let's just take a truck as an example. You got this piece of machinery that weighs, let's say, 8,000 pounds. I'm going to need an engine that weighs itself 1,000 pounds to be able to pull both it and the truck and move the whole thing at the speeds and the torque and the power that I want it to, and be able to keep up in high-speed traffic, be able to pull things like tree stumps out of the ground. I do actually love that truck. I'm not really much of a truck guy, but same thing goes for your house. You want to take the enclosure that you have planned and put into it an engine that will heat and cool it and dehumidify it potentially as effectively as possible. And it is not true that the bigger the better. That is a total misconception about anything that has to do with conditioning or controlling home performance. This is all about customizing and really tailoring the fit. So we're talking about tuning when we talk about home performance on this channel, and tuning is what you are doing with your heating and cooling system in this conversation. So if you want to really break it down simply, what you need to do is take any of the heat that you are losing in the wintertime and replace it one for one, right? Any heat gets lost, you need to put it back in. In the summertime, any heat gets beamed into the house, you want to be able to take it out. That's all you're doing, basically. So one of my favorite things that ever was said in a phone call where somebody was really mad at me for talking about how you need to do a load calc is that if the enclosure is perfect, if the skin is perfectly airtight, perfectly insulated, and when I say perfectly, I mean very, very insulated, way more than would be practical, you don't need a heating or cooling system. That is a theoretical truth. Once people get involved, that goes totally out the window, because of course people are going to open and close the door. They're going to open and close the window when they feel like. Little kids are going to leave the door open, things like that. So some of this is the model needs to be proven out by the actual performance of the actual house in real life after you've done the model. That's why you want to work with somebody generally who's done quite a bit of these. So all you have to do is just add up all the weaknesses. That means anything that's a window that's not very insulated, any of the air leakages that you've got, any places where insulation is missing, things like that. And then the computer tells you how much you need to make up for that. Now, you will be using a computer for this. Essentially, the people who write the standards on this, and Manual J is written by ACA, which is the Air Conditioning Contractors of America, ASHRAE, which is the American Society of Heating, Refrigeration, and Air Conditioning Engineers, has their own standard for this. So you can use kind of either of those. But both of them say that you can kind of make some assumptions about heat losses and gains on paper if you are in a very, very tiny portion of the United States. And in general, I don't know about the rest of the world, but just use a computer, because the problem is that you're trying to figure out for 8,760 hours during the year, what is the coldest and the hottest that you're going to get. And a lot of that has to do with the angle of incidence of the sun. And you can't do that kind of thing on paper and remain sane. So you want to add up the stuff about the enclosure, the interior gains, which is people, cooking. You got a lot of servers. You're going to be putting in a man cave, and you've got a lot of electronic equipment. You're going to be having dance parties, things like that. You want to put that in there as well, and that goes for the cooling. And then you want to equalize those gains and losses with the equipment. So essentially, heating and cooling wise, what we've got is air conditioning. Heating could be your furnace, your boiler, your radiant heating in your floor, your pellet stove. A little harder to control and to be consistent about that. But HVAC stands for, of course, heating, ventilation, and air conditioning. And you want each of those to be controlled within a house. The Manual J, or the load calc that we're talking about today, is limited on the terms of the ventilation, but we could talk more about that later. I've got lots of videos on ventilation, so feel free to explore our channel. So the first thing that you want to understand is how heat flows in homes. I'm not going to talk about anything that's not useful to you in your actual practice of understanding this load calculation topic, but you need to understand that there are three ways that heat flows. First is conduction, which is I put my hand on a cold wall, and the heat in my hand flows into the cold wall. Heat always flows from the highest temperature to the lowest temperature. So the warmer something is next to something that is colder, there's going to be a lot more beaming of heat flow. If you think about how the space shuttle works, it's like negative, I don't even know, hundreds of degrees out in space. And inside the space shuttle, they're trying to keep it, in a nice balmy 70 degrees. That's a lot of what we call delta T. If you want to be nerdy about it, that's the term that people will use. Temperature difference is what that means ultimately. So when you have a greater temperature difference, you're going to have more heat flow. It's going to beam faster. And so you're going to have to control that now. The other thing is convection. So aside from surface-to-surface touching, you've got fluids. And one fluid could be considered liquids, which is water and things like that. But another fluid is what we are in. I always think it's interesting that we used to burn stuff a lot. There'd be torches, there'd be campfires in civilization, right? Back in the BC era. And we were very aware all the time that we were in a fluid because smoke was swirling around us all the time. It was very smoky. And now we're very sterilized. Smoking is banned in a lot of places. So you're not aware of the fact that right now I'm in a fluid and it's moving. And that has a big effect on how comfort works inside homes. And the third thing is radiation. This is mostly, when we're talking about this kind of stuff, the sun. But also, if you're inside of a house at night and the sun is down and you can see outer space, there is heat beaming from your body out through the window and into outer space. It's just a line of sight kind of a communication. So that's kind of a magical thing. But we're going to talk about that in just a second, how to control it. So when we're talking about something like a radiator, which is what you've been looking at in this picture for the last couple minutes, the radiator is involved in all three of these things. It is warming the air, which is literally surface to surface, at which point the air becomes warmer and it starts to convect the fluid motion. And also the term radiator might give you a little hint. It's going to radiate its heat into the room. So if you are able to see it, if you're standing like this and the radiator's over there, this side of my body will become warmer than this side. So I have to turn myself to get this side cool. So that's all kind of just basics that you need to understand. Now, in order to control this, and in general, we're talking about slowing down the heat bleed that is going on in homes. And a lot of that is what we're trying to do with this load calculation. If you're trying to slow down conduction, you use insulation to do that. If you're trying to slow down convection, you use air sealing to do that, or duct sealing to do that. You want to make sure that where air is moving, that it's contained within these kind of very specific areas, and you design that convection. And if you're talking about trying to control radiation, then you're using something like a radiant barrier, which is like a space blanket, mylar, silver sheet, or a low E coating on windows. And you have to know about all this stuff to be able to work this software. So you're going to hear something called the 99-degree design day. We generally just shorthand it design day. The design day is the coldest or hottest day that is going to be experienced in the place where your house is going to be built. But we don't use the absolute hottest from records that are kept. We use the 99% hottest or coldest. That's really important. So you want to pick the 99% coldest day. And again, you can find all of this stuff online. You want to go to one of those two resources that I already mentioned, ASHRAE or Manual J, and you can find this information freely online. What is the 99% design day for your location? This is a big red flag generally. People use the 100% rule a lot, and that's one way that you can kind of game the system. You also need to understand how tonnage works. When I say that an air conditioner is a ton, what I mean is, back when we used to use ice to cool things, it would take a ton of ice, literally 2,000 pounds of ice, and it would transfer 12,000 BTUs per hour, BTUH. So if we take that as an example, if I have a 1.5 ton air conditioner, it would be 18,000 BTUs per hour, or 18 kBTUH. 18,000 BTUs per hour. Again, 2 tons, 24, 2.5 tons, 3 tons, 3.5 tons, 4 tons. You generally, in residential, you're going to go from 1.5 tons all the way up to 5 tons. 5 tons is 60 kilobTUs per hour. That's about the biggest residential system that you're going to find. So knowing how to translate that is important. You'll have a lot of people who say, well, the Manual J says it's 2 ton, but we're going to install a 2.5 or a 3, just to be sure. You want to make sure not to let that happen, because the idea behind this software is you do the calculation, it gives you the number, you install the number, that's it. So temperature and humidity are different things. What we were talking about when we talk about sensible heat is the temperature that I can see on a thermometer or a thermostat. Latent heat is the heat that is available in the air if I were to do what's called phase change. Change the liquid that's in the air, which is vapor, and condense it into water. It would make the area around it hotter. That's what the way sweat works, is the opposite. You have sweat on your arm, it evaporates, and it cools down the environment around where it was, which is why you cool off when you sweat. So when you've got vapor in the air, when it's humid in the air, it's potentially going to make it a lot hotter in the house if it were to condense. So that's why sensible and latent is a thing. Now you'll hear about a sensible latent split, which is an important thing to understand when you're talking about load calculations. Sensible latent split is the amount of power that the air conditioner, generally, the air conditioning coil, is going to put into lowering temperature versus lowering humidity. So if you've got a 75-25 split, then what we're talking about is 75% of the power of the air conditioner is going to be making it cooler, and 25% of it is going to be making it drier. Depending on where you are in the country, this might make sense or not. If you're in a drier region, then you might want a lot higher split. You might want a 90%, 10% split. The ductless mini split that's right here off camera in my TinyLab has a sensible latent split of 95-5. That means 95% of the power that this thing is using is going into making it cooler, and only 5%, which is not enough in most places, is going to dry the air, which is why over there, and you can see a tour of this TinyLab in a separate video, I have a dedicated dehumidifier. Because we're relying on just the air conditioning system to dehumidify the space all the time is not actually a really good idea, which is what I'm going to get to in a second. So the highest absolute humidity used to be understood to be also the highest temperature. People used to think that if you design an air conditioner for 95 degrees, which is your 99% design day in your area, which I used to be in Chicago, and I think that 95 was the 99% design day, then I would also have the highest humidity on that day, and I'd be able to tackle both. What they found when ASHRAE did a study on this is that that was absolutely not true. Actually, the highest absolute temperature, and absolute humidity, when we say relative humidity, what is relative about that humidity is the temperature. If it is 100 degrees and it's 100% relative humidity, that's a lot wetter than something that's 50 degrees, 100% relative humidity. It's raining at 50 degrees, raining at 100 degrees, totally different amounts of actual water that we're talking about, because warmer air can hold more moisture. So when we talk about absolute humidity, we're just talking about how many grains per pound. There, you don't need to remember that, but that's just the units that we use. So it turns out that the highest absolute humidity is at a lower temperature, let's say something like 83 degrees or 85 degrees. And your air conditioner is not going to be as stressed out because it runs, as you know, your thermostat shows temperature, not humidity. So if it's 95 degrees, your air conditioner is really taking it seriously. If it's 83, your air conditioner is not taking it that seriously. So this is what your reports will look like. Not very fun to look at. Generally, if I'm giving my clients one of these, it's going to be like 20 pages. And even I don't want to read through the whole thing. I check my work before I press print on this thing, and then I'm like, okay, great. Now I can get this out of my hands and give this to somebody else who might want to look at it. That's a lot of numbers. It's a lot of graphs. It's a lot of tables. There are some pretty colors, which is nice. I'm going to get more into what all these pretty colors and these graphs and tables mean in a few minutes. So why would you want to do this? Now that you understand the basics of how heat flows, the difference between the enclosure and the engines, things like that. First of all, rules of thumb do not work. What people used to do is just look at a house or ask you how many square feet your house is, and they'd say, okay, that sounds like a 2-ton or a 5-ton air conditioner. When I was first starting out, I had a mechanical engineering firm, very well respected, tell my client who was building an 800 square foot high performance, very well insulated condo that they needed a 5-ton air conditioner. That was the beginning of my journey into telling mechanical engineering firms how this works, because a lot of them are using a commercial software which has nothing to do with residential. So don't let somebody use something like, for example, there's a software called Train Trace. That's a commercial building software. You don't want to be using that for residential because they're totally different, which is partly why I don't work in commercial buildings. I only work in homes. They're just different things. So the rule of thumb used to be, you got 500 square feet of space, I'm going to give you 1 ton of air conditioning. And the heat kind of pairs up. Generally, you're gonna have the air conditioner sized, then you're going to pair that with a blower, a fan that's going to move that air, and then there's going to be a furnace that matches with that. And nowadays, people have 2-stage furnaces or 2-stage air conditioners or variable furnaces, things like that. And that way, we can still install something that's much bigger than it needs to be, which is more expensive for the buyer, for sure. And that's incentivized for me. If I'm selling you this system, I want to sell you a bigger one because that makes a lot more money for me. Anyway, we can have you have a bigger one and then just dial it back and you'll be fine. That's kind of a scam if you think about it. So let's take that seriously. There are reasons to oversize for reasons that I'll get to in a few minutes. But nowadays, if there is such a thing as a rule of thumb, which there's not, so don't believe this, but if you're building a house that's going to be relatively high performance, meaning it's going to be meeting energy codes, if you are in a state that has energy codes, then you're looking at something like 1,500 square feet per ton. So if you used to have a 1,500 square foot house, you'd have a 3-ton air conditioner. Nowadays, you would have a 1-ton air conditioner. They don't even sell 1-ton air conditioners sometimes. So you want to be able to understand all that. Okay, good. Yep. So once we understand the rules of thumb and how to avoid them by doing a load calculation, you want to understand what happens if you don't. If you undersize your system, your heating and cooling system is smaller than it needs to be for your house, which is rare, but it can happen, then your house gets beat up on by what's happening outside of it, which is weather. When the temperature swings up, let's say it's, May, and overnight it's 50, but then first thing in the morning, as soon as the sun comes up, it gets to be 80 degrees. And that happens in a lot of places around the country and around the world. If you're in the desert, that's even crazier, right? Then suddenly your house has to really work hard to make up for that over hours instead of having to really track well. Now, if you have it oversized, that's a totally different problem. Your house gets beat up on by the stuff that's happening inside of it, which is your furnace turns on and it immediately punches your house in the face as hard as it can. And your house goes, oh my gosh, it's so hot in here. Or likewise on the cooling side. And that also is not good, partly because of dehumidification problems in the summertime. The humidity issue is that an air conditioner needs about 10 minutes on average to start drying out the air. It needs to get cold enough that it's going to really start wringing out the moisture from the air and get soaking wet and then start draining that stuff to the outside. Because if the coil gets wet and then the air conditioning system turns off, what happens to all that water? It re-evaporates back into your house. And now you have done zero dehumidification. So the humidity issues that we're talking about are going to be a problem as we keep building because newer codes are requiring tighter houses, better insulated. We basically are making these houses very tuned for the enclosure. But if you are not actually enforcing the code requirement of load calculations, then we're going to have major problems with this humidity issue because we are going to have oversizing. So the component loads, when you're looking at how this stuff works and why you want to do this load, is to understand partly what is going on in your house. What is sucking the most heat out or adding the most heat to the house? I've got two different buildings here. On the left, you have a typical building. This is a home, by the way. When I say building, I mean house generally. So you've got the building loss, which is the bleed out in the wintertime. And that's about 100,000 BTUs per hour. That's the size of the furnace that somebody would be wanting to install here. And the gain in the summertime is 74,000. That's over 6 tons. So you're gonna need 2 systems in that house. And you might even get sold 3 or 4 systems, depending on how sprawling your house is. The number of systems, I'm not gonna get into too much. Suffice it to say that my new house, my 3,000 square foot house, has 1 ducted system in it. So you do not need to do multiple systems just because somebody tells you that that's the most sophisticated way. That's just another way to sell you more stuff in a lot of cases. Again, there are exceptions to all these rules, and you want to make sure that the person that you're talking to is a true professional who really has a good track record, good references, and all that stuff. So you can see that glass, which is the red slice of the pie here on the left, is 22% of my bleed out in the wintertime and 40% of my heat that's added to the house in the summertime. And this, by the way, is also to do with the design stuff. So when we're talking about the amount of heat that's added, it's that over that 8,670 hours, but you're also kind of considering daytime is very heavily weighted in the summertime because the sun coming up is going to add a lot of heat. Not just that it's 90 degrees outside, is that the sun is like trying to beat your house down. So that's on the left. You've got infiltration, which is purple. These are the things that you won't see so much on the right. Infiltration is 22% of my loss in the winter, 12% of my gain in the summer. That's a pretty leaky building. That's typical. Walls, you can see. Roof, you can see grows a tiny bit in the summertime. The ductwork becomes a big deal. I can tell by this graph that the ductwork is in the attic or in a crawl space, but I don't see floors on this list either. So floors is like 9% in the wintertime. All that's to say, you can look at this when you understand how the enclosure works enough, and you can kind of tell what shape and size the house might be based on these graphs. It's kind of a fun thing. On the right, you'll see a totally different signature. So you'll see that glass is a much smaller piece of the pie in the wintertime, and it's a much bigger piece of the pie, like proportionally, basically. The swing between winter and summer becomes a much bigger deal. Infiltration is really not even on here because this is a very airtight house. Ventilation, so purposefully bringing air from outside into the house, becomes a cost, a bleed here. So you can see this 9% in the wintertime, 21% in the summertime. 1/5 of all of the cooling I'm going to need to add to my house is because of fresh air. But I need that fresh air because healthy is the number one thing that I want my house to be, not necessarily just energy efficient. You can see that equipment adds heat in the summertime. So basically just looking at this, and we're going to get a little bit deeper into this in three specific cases later. This is kind of an interesting place to start. So this is where you can start to use the Manual J software or the load calculation software to do some engineering for you, to find out like, well, okay, what if we built a house that's a little bit better insulated? Would that save me a ton on my air conditioning? In other words, if I can spend $1,000 more on insulation, which is cheap, only needs to be done one time and draws no energy over the course of its life, could I save a ton of air conditioning, which is expensive upfront, which needs to be maintained and replaced and draws energy, right? That's an easy decision to make. So this is how you do that. Now, window placement becomes a very big conversation. There's another hidden thing that I'll get to in a second, but the windows, where they are and how big they are is very important. If you decide that you just have to buy a lot that's on the east side of a lake, and it's got the mountain range behind the lake, and so you're going to be looking out that west wall, and that's your big wall where you're going to have nothing but windows. That is a terrible plan when you're talking about heat loads, because you have what's called an adequate exposure diversity, AED. What this means is basically you got the green line in both of these graphs, which is the average of cooling. The AED only has to do with cooling, because the sun only has a negative effect in the summertime, in the hot months. So you take the average, and then you're going to add 30% to that, and you do not want to exceed that 30. 30% is the blue line. If you exceed that 30% of the average, then that means that you don't have good diversity of placement of your windows. The windows are too heavy weighted on one side of the building, and you need to basically move them around a little bit, make it even. You can see on the left a well-designed window plan where it does not exceed the blue line, and on the right, a terrible plan, which is where it exceeds the blue line at about 4 o'clock in the afternoon. It's going to exceed it by 14% on top of the 30. So that's not good. We want to make sure that that is not the case, because in this case, we've got 8 a.m. on the right. We're talking about something shy of 3,000 BTUs per hour without the sun coming into effect. Once the sun comes up and starts hitting real strong, you can see it rises, and then by 5 o'clock, I've got over twice the amount of cooling that I needed in the morning. That means I'm going to have to install twice as big an air conditioner, in theory, than I should have to. So we don't want that, because now you've got one that's oversized all the time, except at 5 o'clock in the afternoon on a summer day. And that's just not good, because how often does that happen? On June 21st at 5 o'clock in the afternoon, yeah, it's going to be doing its job, but the entire rest of the year, it's not going to be doing it. So again, adequate exposure diversity is what that's called. Another reason why you have to do this is it is law. In all states, it will be law ultimately, because there is no other way to build. I have a book called Home Performance Diagnostics, and I wrote that in 2012. And all I have to do is wait, because everyone will have to test someday, because there is no other way to tune home performance in homes that are becoming increasingly tighter, in homes that are increasingly well tuned, then to test them and figure out what exactly they're doing. It's the same as vitals, right? So what you want to do is make sure that you are ahead of this state code, because if you wait until it's state law and then you start learning how to do this, it's going to be very, very stressful for you. Also, if you are a homeowner in one of these places where it is state law and you have a system where they didn't do some of the things that I'm going to talk about, then you have potentially a lawsuit that you are available to pursue. So this is going to be state law for new homes. You also want to make sure that if you're building an addition that you have the load calc done, because often you've got a system that was installed in the 80s and then many things happen to the house. You might have replaced the windows. You might have added more insulation to the attic. You might have then done this addition. You might have tightened up the house with an air sealing project. And now the size of the air conditioner that you had in the 80s and the size that is needed by the house, completely different. Not in the same ballpark at all. So this is also important. And then gut renovations, obviously. If you're changing anything about the characteristics of the enclosure, the skin of the house, the air sealing and insulation layer, you want to make sure that you're having this done. And then generally what's called a push-pull is when somebody comes in, takes a 2-ton air conditioner, puts 2-ton air conditioner back in its place, that's brand new. That's not going to work because I already mentioned houses go through changes. You're going to be replacing your windows, you're going to be adding insulation, things like that. So you want to make sure that you have this done. How do we do this? So first thing, you need to either have building plans or you need to go to a house. In either case, this is going to take several hours to do. If I'm going to go to somebody's house, what I need to do is I need to measure out every single wall, floor, and ceiling. I will be building a 3D model out of this information. I need to know the placement and size of every single window in the house. And I need to know the insulating factor of the walls, the ceiling, every window, et cetera, et cetera. In a lot of cases, if it's an existing home, I'm going to be assuming a lot of that. So the air leakage is the last piece of this puzzle, and this is really important and really interesting. You have 3 options in most softwares. You could say that the house that you're modeling is leaky, it is average, or it is tight. I do blower door testing for a living. I have been in hundreds of homes checking out their air leakage. I have no idea what any of those words means, because average for what is the question. So don't use those inputs. If you're going to be using the software, just avoid those at all costs. You want to put instead the blower door test number or the air changes per hour that you're aiming for. If your state requires 3 air changes per hour, 3 is a magic number because it's the cost, it's like the point of diminishing returns, basically. So if you build a house that's 3 air changes per hour, the equipment is going to be largely the same. The infiltration, which is the air leakage, is going to have about the same effect, which is minimal, from 3 down to 0. You could build a super airtight house and it would basically have the same effect on the air leakage's cost for heat bleed as if you have one that's 3. So you just know what that number is that you're aiming for. And then also you need to put in the mechanical ventilation, which is forced, like intentional, air leakage to outside. And that's generally 24 hours a day. Something that is not just a bath exhaust fan, because if you have, every house should have bath exhaust fans, just turning on the bath exhaust when you take a shower, that does not go into this software. Don't put that in there. So here's the 3D model that I mentioned. You're going to have to know like the ceiling area of each room, the wall area of each room, the floor area of each room. And all you're paying attention to is the enclosure itself. I do not care about interior walls because it's what's called adiabatic, which means that it's the same temperature on both sides. It's that delta T issue that we were talking about earlier. All you are doing with the software is trying to figure out how much heat is bleeding out of or into your enclosure. You don't have to model interior anything. That being said, what I could do here is 2 different kinds of load calculations. I could do what's called a block load, which is taking this rectangular floor plan and then just multiplying it by the ceiling height of the entire thing and doing one block. That would be one big cube. That's called a block load, and that gives you the heating and cooling necessary for this entire place. That is not going to tell you the whole story, because at that point what you need to do is take this report and build a duct design out of it and install actual ducts and registers, and you're just guessing. If you just say, okay, well that room is bigger than that room, therefore I should give it, let's say, 20% more heating and cooling than the other room. But I'm not paying attention to my window placement, which way is west, and all that stuff, and you could definitely screw that up. What's better is a room by room load, and that is what we're doing here. In general, from now on, I'm only going to be talking about room by room loads, because block load is something that you can just do if you just want to know how off is the system that is installed in this house. Great, do a block load. If you are like, hey, maybe I should replace my system with something that's smaller, do a block load. Great, that's fine. But if you are going to be doing any duct design or duct installation, you want to do a room by room. When do you want to do this? Always beforehand. Really important, because once the equipment is selected and installed and selected, once you select the equipment, you're going to be doing the duct design. Once the duct design is done, you can't go back and redo the equipment. So you need to make sure that this is like the beginning of the process. I have been asked to do manual J calculations that will result in a 2-ton air conditioner, because that's what we already installed. I do not do jobs like that. And so generally, you can do that. And that's part of why I'm doing this video right now, is because there are lots of ways to game this software, accidentally or intentionally, to make it say whatever I want. And that's why it's important for you to know how this works, how to read somebody else's report, and how it can be cheated and gamed. So you want to make sure that you want to do it before the windows and the insulation and the air tightness details are all decided, because you can now make decisions about that stuff. You could say, well, for example, TinyLab, I have a small heat load, and you're going to see that in a little bit. I could insulate this place better, but why would I do that? Because I still have to select the same exact, I'm dealing with like drops in the bucket at that point. So if I can go from a 24,000 BTU per hour heat loss and go down to 22,000 with some extra air sealing details that are going to cost money, I still have to install a 24,000, because that's a 2-ton. They do not make air conditioners that are 22,000. That's a bad example. You probably could find an air conditioner that would deliver 22,000 because they float around those numbers, that 2-ton, 3-ton, 2.5. But all I'm saying is, if you have to install a certain piece of equipment, making more expensive decisions on air sealing, on insulation, on windows isn't going to make any difference for you, because you still have to buy this thing. So now we're just talking about pennies of utility savings. And it's the opportunity for you to tune this home as a system, because the home is a system. Always remember that. Everything to do with the Home Performance channel, with our television show Home Diagnosis, is about that. Everything in your home has to do with everything else. Who should do this? This is a very important question. Think about the person who's going to be operating this software. I already told you, we're not doing this on paper. We're doing this at a computer. So someone is going to sit down at a computer and spend hours building a 3D model and then putting a bunch of numbers into a software. They should be comfortable with computers. Generally, you're also want to make sure that person has blower door test data and they know what a blower door test is. Think about a lot of HVAC technicians across this country. They are not, and I'm not saying this to be mean, I'm just saying it because it's true, they're not given the tools or the training to understand a lot of this stuff, and they are not very comfortable with computers. If someone can't write you back an email that's not in all caps, maybe they're not very comfortable with computers. And you want to make sure that they are very accurate, because again, lots of ways to accidentally screw this calculation up. The last thing is, if you deem this appropriate, having somebody who is not the HVAC installer, who's actually going to sell you this system, do this calculation because they don't care how big the system is, might be a good idea. And that's part of why independent consultants like me exist. So here are some examples of load reports that are real. First of all, the TinyLab, what I'm talking to you from right now. This is the basic layout. Again, you can see a tour of this house, and you can get really deep. We have over 60 videos of the construction and fine-tuning of this place. It's weird. I'll just say that. It's a weird thing to have a house on wheels. And again, I do not recommend it for most people. That being said, we were going to tour this house all over the country, but I had to pick a place for the Manual J. You have to tell it like one location that you're going to sit this house, because the sun, they can't figure out like, oh, it's going to be great in Alaska and in Atlanta. So you just got to pick a place. So we picked Atlanta because we knew we were going to settle here. And the front door faces south for a reason I will tell you in a moment. You can see here that I've highlighted a couple of things. The things that I want to draw your eye to are the other pink things on this, which is the outdoor dry bulb. In winter, 22. In summer, 92. That is the 99-degree design day that I was talking about earlier. So in the wintertime, it's not going to get any colder, according to the design, than 22. It will get colder. On one day, it will be like 10. And on that day, and this is for you to take into this winter as you're sitting in your house, if your heating system is not running 24 hours a day nonstop without cease, then it's too big. Isn't that an interesting experiment? Likewise, in the summertime, if you have a day that exceeds 92 degrees, if it suddenly becomes 96 degrees here in Georgia, I would expect for my air conditioner to run nonstop for 24 hours straight. And if it only runs for 30 minutes out of every hour, it means it's oversized. So that's what that's for. Now, here we can see that what's called check figures. This is a place that's going to be in the first couple pages of any Manual J calculation, load calculation. It's going to tell you a couple pieces of information that you could definitely use to just really quick figure out whether this makes any sense at all. First of all, square feet of room area, 173. Yeah, it's crazy, I know. But that's what I'm sitting in right now. The volume of this place is about 1,600 cubic feet. To give you an example, my house is ventilated because it's so airtight. You always want to have ventilation. The ventilation rate is 30 CFM, 30 cubic feet per minute. So over the course of an hour, we take 30 times 60, and I get 1,800 cubic feet per hour. That means that I'm replacing all the air inside of this house once an hour, every day, 24 times a day. Isn't that interesting? So square foot per ton is the thing that I also have highlighted here, and that's 679. I told you earlier that when you have a high performance home, you're looking at like 1,500 square feet per ton. The reason that we're at 679, which is very low for such a high performance house, is because of equipment selection, which I'll get into later. So we have some heat bleed around here that I do not care about, and it's excessive for a house of this size. But again, I don't care. The heating required, including ventilation air, that continuous ventilation that I'm bringing in that I just mentioned once an hour, 4,000 BTUs per hour. The cooling required, including ventilation air, 3,000 BTUs per hour. A ton of air conditioning is 12,000 BTUs per hour. So I'm at a quarter ton of air conditioning needed for this house. So if I was to make this 679 square feet per ton be 1,500, I would take my cooling required down to, let's just say that I multiply the square feet per ton by 3, and I cut my cooling required by 3 as well. So now I'm at 1,000. Now I'm at 1/12 of a ton. What I have done at that point is intentionally and very dumbly detune my enclosure from my engines, because I don't want just my enclosure to be tuned and my engines to be tuned. I want them to be tuned to each other. So I want my air conditioning system, which I can only buy at the smallest, 6,000 BTUs per hour, a half ton, which is what I've got here. That's double oversized already, but I can't install less than the 2x4 insulation I've got in the walls because I would feel bad about that. So I've got a system that's already double oversized. If I keep on insulating this place and make it more efficient, it's just I'm gonna have to still buy the same tiny piece of equipment, which is the smallest one they make in the world. So there's a little bit of the experience. You can use the software, but you have to understand what it means in real life after you are done with the report. So your summary loads, you can see on this page right here, we've got all of the pieces of the building broken down into one list. You can see that I've got double glazed windows. The glazing is the glass. Double pane windows with low E coating, my one door, my framed wall with R15 insulation in it. It's 2x4 construction. Roof is 2x4 construction as well, blah, blah, blah. You can see the areas. You can see the sensible loss. That's that temperature loss. You can see the latent gain, which doesn't matter until you get all the way down to the ventilation rate. Now I've got latent gain happening. You can see the infiltration is modeled as basically 0, which is about right. The blower door test on this house is 50. So I get at the bottom, I've got my 4,200, my 690 latent problem, my humidity, and my 2,300 sensible gain, with a total gain with the sensible plus the latent of 3,000. So that's how that breaks down. It's basically everything just added up together. What it means is this. These are the kind of pie graphs. So 100% would be all these added together. You can see my walls are the biggest loss for me in the wintertime on the left. They're a significant gain for me in the summertime. My ventilation, though, is monstrous. It's almost as big as the wall heat bleed. But that's unavoidable. Again, healthy home is the most important thing to me. So what you don't see on this is infiltration, air leakage, because the house is super airtight. You will replace that with ventilation because that's what you do. When you build airtight, you then have to forcefully bring in outdoor air. And you'll see the same thing on the big house that we're building. Now, the reason my front door faces south in my model is this. You could see that when I move this house, and this house does move, that's one of the really cool things about this, you would use this graph to like place your house on your land. If you have, let's say, a farm and you could face it any direction you want, you would pick south to face it. Of course, I'm driving this house around all the time, and so when I drive it and I park it somewhere for a week, I need to know which orientation to put it in so that I can make it as easy as possible for my equipment to do its job. This front door faces south is the best. That means that I can keep my 0.25 tons. But you can see that the difference here is not very much. We're going from 0.25 tons, a quarter ton, up to 0.32 at the max. If I had my front door facing east and I get all that sun beaming in through the west at 4 o'clock through 6 o'clock in the summertime, even then I'm at a third of a ton, not too much of a problem. So you want to kind of take the scale into account as well. And here you can see a lot more interesting piece of information, which is all of the different ways that the house will interact with the sun. So over the course of the day, and in general, when you're looking at graphs that are like this, it's going to be from 8 a.m. when the sun comes up in the summertime to 7 p.m. when the sun is going down. And again, you know, it doesn't get dark until 9, but that's long past when the sun is going to be hurting the heat gain of your house. So you can see that if I face it that one way where it climbs from 8 a.m. all the way up to the top, where it's a third of a ton at the end of the day, that's the way I probably don't want to do that. Not because of energy efficiency or because of trying to get my equipment to do what it wants, just because if I start stressing out my house and stretching it and trying to make it heat up and cool down, it is against what is balanced. Right? So if we're talking about tuning, you want to try and make everything like smooth and calm, like Zen. So that means trying to shade your house from real major spikes in heat gain and heat loss. So now that we've gotten through the TinyLab, I want to show you another tiny space that is not designed like this one. This one is designed by a designer. I designed the TinyLab, and of course it's designed for performance tuning. This one did not have performance tuning in mind, and in fact my task here was to take this design, which is essentially a prefab home. It was very beautiful. If you think about like basically a fiberglass pool structure that's very intricate and cool, and then you just flip it upside down and you cover it with dirt, it becomes basically a Hobbit house. If we were to do that and ship it all over the country, can we meet energy code in all 50 states with this design? People could turn it in any direction they wanted to. They could put whatever kind of soil they wanted to over the top, whether they're in the desert and it's sand, or in in Minnesota and it's really, really wet soil. So they wanted to know if that's possible. So here's the back. There's a window you can see there, a little circular window, a bigger window, a small window sticking out, jutting out on the left there, and then a more medium-sized window on the right-hand side in that little dormer. And this is where a lot of the windows actually live. So the big, huge sliding glass doors, the front door, etc., lived on the other side of the house inside this L. So here's our check figures. So we're going to look at this again, and I'm going to just draw your eye to a couple things. First of all, the square footage of room area, 625. Bigger than my house by multiple times, but still a very, very tiny space. And anything that's less than 1,000 square feet is going to act a little differently than a normal house, and that's important for people to understand. The volume is 6,500. Generally, one quick check that you can do is take the square footage, multiply it by 10. That'd be 6,000. Is the volume about that? Yes, good. Now we're talking. If the volume is considerably different than 10 times the square footage, you want to know why. That's a question mark. That's a kind of a red flag at that point. Square footage per ton, 1,000. pretty good. That means that it looks like they've done a pretty good job speccing the insulation and all that stuff for this. Total heating required, including ventilation air, 7,000. And we've got cooling of 7,500. So the cooling is actually higher than the heating. Very interesting. Part of that is to do with the fact that it's underground. And also ventilation, right? We're going to talk about that in a second. So we've got like a half ton, a little more than that. 3/4 ton air conditioner would probably be what was specified here. You won't have a lot of air conditioning companies really happy to install a 3/4 ton system on this house, because what if you have a dinner party at 5 o'clock at night on a summer's evening and you've got the door wide open? What's going to happen next is you're going to call that HVAC installer and you're going to complain. So they want to avoid you complaining to them. So they're going to install one that's much bigger than you need, because just in case you screw up and you have a party at 5 o'clock in the evening on a Friday afternoon in the summer, they don't want you to call them, and they want the system to be able to keep up with your mistake. So therefore, let them know that that's what they're dealing with, is that, like, you're smart, you're not going to have a party, at 5 o'clock in the afternoon on a summer day. So here's your load, your component loads. Building loss, most of it glass. Building gains, most of it glass. We have a problem here. So obviously there is just too much glass in this equation. The wall, which there is the most of, if you notice the shape of this house, there's really hardly any ceiling because all of the walls are sloped. It's like, what do they call that? It's like a barn, you know what I mean? So the walls go up and then there's this little tiny ceiling. So most of the thing is walls or floor. So you can see the floor is 12% of my loss. The floor in the summertime, and this is one of the reasons why putting insulation underneath your house, under the slab, is one of the last things you do. In the summer, your floor actually cools your house. It is a benefit to you that it's uninsulated, that it is connected to the house. It becomes a heat sink. So you will never see it on the summertime issues, on the heat gain here. But we can see that we've got a little bit of a problem. Also, AED excursion on the right. That means that we have windows that are out of whack. We need them to get more well distributed. So here's our rotation. We can see that we go from a little over a half ton to about 3/4 of a ton, depending on where I put my house front door. Now this is okay. You can have this happen, but the goal of being able to turn this house however the buyer wants is absolutely out of the question, because you can't have the same exact system go into this house and act the exact same way in a consistent, predictable way. And predicting is a big part of what home performance tuning is about. I want to know what's going to happen in this house if they turn it to the west versus to the south. So here's that adequate exposure diversity. You can see that the heat picks up at 8 o'clock and it starts growing, and by 5 o'clock in the afternoon, it is huge, much different. This is the one that I was showing you earlier. So obviously, this cannot be turned any way. It needs to be redesigned, and that was my advice to this company. Here's our high performance house. So this one, again, designed by us. We had an architect help us out with the aesthetic issues and the flow of the house and all that stuff, which we're not experts in. But as far as performance, this place is definitely designed for this. So here's the basic layout. Again, you can see lots and lots of videos. I think we've already exceeded the TinyLab playlist on this one. And we've done some pretty outside the box testing on it so far too. So let's do our check figures on this. We've got 5,000 square feet. I told you it was 3,000. What's going on? Well, this software, a couple things. Number one, you got rooms that are 16-foot ceilings. The software may, either in a hidden way or in an obvious way, make that into 2 8-foot rooms, because it's not designed. It's designed to contain enclosures that are normal ceiling heights, which is 8-9 feet. In fact, that's written into the standards. So when you have a 16-foot high ceiling, it's totally different on the volume. So the volume is 43,870, which is on the nose what my actual volume is from my 3D model. That's good. The other thing that goes into the square footage here is my crawl space, which I don't count into my square footage of my house because it's a 4-foot crawl space. It's basically a mini basement. It's totally enclosed inside the house, insulated. It's going to be the same temperature and relative humidity as outside, but it has no windows, which obviously is a big benefit for it. It is insulated underneath and on the walls, and it's not going to have any people down there. And it's one big room, so it'll basically adjust itself very easily. I only have to really have one supply down there. The the square footage per ton, 3,000. Again, that is not real. That's taking my crawl space into effect as well. Really what we're looking at here is, something like 1,600 to 1,800 square feet per ton, which is really good. The heating required, including ventilation air, 37,000 BTUs per hour. That's the whole house, which is two separate pieces. I'm going to get into that in a moment, but we've got basically the living space, and we've got a studio space, which is for music and dance. I used to be a musician. My wife used to be a dancer professionally, and we want to be able to do that in our grown-up life. So the studio is its own self-contained, insulated on its own, has its own ventilation system, its own heating and cooling system, etc. So what we're looking at right now is what's called the block load, which is all of that put together. So 37,000 BTUs per hour heat, 20,000 BTUs per hour cooling. That's a ton, a ton and 3/4 of cooling, shy of 2. And you can see my split here. The sensible latent split for the entire house is 77-23. I'm going to be using one of these pieces of equipment, the ductless mini split, which is a 95/5 sensible latent split. So that's not going to be good. I definitely need to be planning for, in any high performance home that's going to be reasonably airtight and reasonably well insulated, I have to have dedicated dehumidification. Just know that going into it. So my design data, Atlanta, right? I've got my same exact 99% design day right down here, which is 2292. You can see my outdoor relative humidity, which in, I think, ACCA's case is still estimated, and in ASHRAE's case is actual weather data. Doesn't really matter. Again, you're going to want dedicated dehumidification. You can see all of this is in line with what you want. So the load preview report. This is, again, what we were looking at with kind of itemizing all of the bleeds. You can itemize all of the individual rooms or zones in your house if you decide to have a zone system, which I'm not going to, because that's not necessarily better just because it's separate. So we've got the system 1, which is my living space. That's the first portion of this right up here. And then system 2 is my crawl space, or excuse me, not the crawl space, the studio. So the living space, you see I've got my crawl space is 1,400 square feet. I have 800 BTUs per hour of gain in the summertime. And that's because some of the foundation wall is out of the ground and it might be taking some beating from the sun. So I now have over here the BTUs required for each room and the amount of CFM, cubic feet per minute of airflow, that I would need for those rooms. And it'll even tell me what the duct size is to achieve that. Now that is not counting the duct design, because if I make something, a duct take a bunch of turns, then I have to upsize the duct because it's going to build up pressure. And that's a topic for a totally different video, so don't worry about that. But you can see that the way that it splits out is I've got system 1 is 1.5 tons, and system 2 is 1/4 of a ton of load. That's awesome. That's what I want. So that is what we're going to be installing in this house. And you can see the CFM over here. I've got a total of 600 CFM that I need to move, which is what a ton of air conditioning, or excuse me, a 1.5 tons of air conditioning moves. A ton moves about 400 CFM in order to get the relationship right where you're bleeding out the heat and the humidity. You can play with that with the speed taps, and an HVAC professional is the one who should be doing that. So here's the way that my component loads work. I've got floor, which is my slab. That's bleeding some. I have 2 inches of insulation under there. I didn't want to add more than that because the cost benefit, again, at this point, I've got a 1.5 ton split system air conditioner. They don't make smaller than a 1.5 ton in a ducted system. And so I have to buy that no matter what. So why would I insulate more? So getting these numbers to be smaller is not necessarily my goal at this point, because I would, again, be intentionally detuning my system. So just take a look at those for a moment. Again, this is the whole house. And I want to show you now what goes on in a house that has windows versus a house that has no windows. On the left, the living space. You can see that I meet my adequate exposure diversity. On the right, my studio space, which has no windows, and therefore the sun has no effect from 8 a.m. to 7 p.m. that is different. There's no variation in what the system has to do. What the difference is going to be is what we do in that space. So if I have a dance party in there, this is going to go off the charts, and I have modeled it with 15 people in that space, and I've done all that calculation. So we have, as you could see in the previous one, we had about a 1/4 ton of load. I'm going to be installing a 3/4 ton system in there, so that I've got it triple oversized, but it's an inverter system, which means it can dial all the way down to meet my very minimum needs in shoulder seasons. Shoulder season is when the temperature outside is mild. So the software demonstration is the next thing I'd like to run you through, just to show you kind of how the software works. I'm going to show you in the numeric format. So let me take you over there. Here's what a load calculation software actually looks like. So you can see a bunch of numbers. We have several windows that are open at the same time. This is kind of the way that I work. Up here, we have our general project data. Each of these is going to have a little explanation, but in general, you're going to need some serious training to be able to use one of these. Here in the system design, I'd like to just point out a couple things. Number one is I've got the design indoor temperature that I want in the wintertime and in the summertime, and the indoor relative humidity that I want in the wintertime and summertime. Each of these is a default value that's based on manual J or ASHRAE standards. So generally you don't want to mess around with this unless you know for a fact somebody's going to be using this place as a grow house, or they're going to have an indoor pool and you want to plan for that kind of thing. Ventilation and infiltration, these are very important. Number one thing to understand about this is that you cannot do an accurate load calculation without doing a blower door test. So what I really want to do is go down to blower door method, which is the right way to do this, and then I can use just a simple single point test. There are some inputs in here that you don't need to understand, but basically you're going to 50 pascals, which is this number right here, and the air changes per hour or the test flow, either one I can put in, that I'm shooting for is going to be in there. Once you hit about 3 air changes per hour, you're going to see a diminishing return. So it's not going to make a huge difference in your load if you go 3 air changes per hour, or if you go like I have gone here, 0.6. 0.6 is passive house levels of air tightness. I'm aiming for that because I like to show off when I build, because I'm a terrible builder, and yet I'm able to do these things because it's not that hard. So I've put this number in here because I know for a fact that I'm going to hit that. Now I can hit OK. I need to go over to my ventilation and adjust my ventilation rate. The ventilation is going to be the mechanical ventilation that is required if you have a house that's tighter than 5 air changes per hour. Almost every house that's built in the country today is going to be aiming for, or maybe accidentally achieving, 5 air changes per hour. It's just a function of the kind of materials that we're using, the kind of workmanship that we're seeing, etc. If you have a really hurried build crew and they're doing a real crappy job, then you're not going to hit 5. You're going to be a lot looser than that. It means the number is going to be bigger. You're going to be at 7 or 9 or 12. But generally, if you're paying attention to things, you're going to end up at 5. So you've got an above grade volume of conditioned space, the number of people in the system, and here I've put in number 17, which is way overblown, because that's for party mode. So one of these spaces is going to be a commercial mixed-use space, as I mentioned. So that means that sometimes there's going to be a dance party in there. A lot of these are going to be default inputs, but generally what you want to see here is something that's in the realm of what ASHRAE 62.2 is going to give you. There's a really great tool online called Red Calcs. If you just search Red Calcs 62.2, you'll find the Residential Energy Dynamics site. I'm going to link it in the notes under this video, but it'll give you a number that's in the low hundreds for no matter what size house you've got. Exhaust, do not put all of the bath exhaust in there, or say, oh, I'm going to run my 50 CFM bath fan. They assume that if you're going to put something in here, it's going to run 24 hours a day. Don't do that. Heat recovery, yes. If you're using a heat recovery ventilator or an energy recovery ventilator, it's going to be yes. The heat recovery efficiency you're going to put in as well. And then you're going to ignore all the rest of this except for maybe the duct load factors. Because if you're going to put the ducts in the attic, then they're going to pick up heat in the summertime. And if you're going to put them in the crawl space, they're going to lose heat in the wintertime, etc. So here you can see we are describing the enclosure. So I've got floor material, roof and ceiling material, wall material, glass material, and door material. And these are all reflected here in the default value. So when I start a new room, I'm just going to basically describe any floors, roofs, walls, glass, or doors that lead to outdoors. Anything that leads to anywhere else in the house is not important. This computer program does not need to know about it. You do not input that stuff. So you can see in my studio space, where I don't have any windows, I have the gain in the studio space being around 1/3 of a ton. That's with only 2 people in there. Let's just see what happens if we take away the people entirely. Now I've dropped it by almost 1,000. You can see that there's no people in here. The ventilation load is the biggest thing that's happening in here, after which the walls are what's picking up the heat from outside. So if I was to add in a party, if I put 15 people in here, then you can see that the people become most of the load in this case. However, this right here shows me that I'm still under a ton of cooling needed. That means that I'm going to be getting a 9,000 BTU per hour or less piece of equipment. And generally those are going to be, I'm going to be buying the same piece of equipment no matter what. So it doesn't really matter to me as if I have 2 people or if I've got 15 people in there, the piece of equipment that I will be buying will be able to do its job. The most important thing to remember about all of this inside the software is if you put crap in, you're going to get crap out. You have to make sure that you're accurate, which is why you have a professional, especially somebody who's comfortable sitting down with a computer and messing around with numbers and trying to experiment with things, do this calculation for you. Do not attempt this on your own, homeowners. And for the HVAC professionals who are out there, the number one thing you can do is to get more comfortable with computers, because a lot of us spend all our time in the field and we don't really like spending time in front of a computer. If you don't want to do this, great. Find somebody who does want to sit in front of a computer and use them for this, because this is a very delicate calculation. So I hope that this demonstration has been helpful to you. Make sure that you subscribe to our channel if you want to know more about home performance and how all this stuff works. Please do comment and like it as well. Tune in next time.